Now let's talk about incorporating risk to the capital budget. And then we're going to basically combine the inflation and the risk into this same problem. So we're a little bit of a digression now, talking about risk, and then we'll come back and combine this problem with the inflation and the risk. Okay, let's talk about it in terms of a certainty equivalent, probability analysis, and then adjusting the discount rate. The certainty equivalent approach, and we'll talk to it a little bit now at the end of this lecture, is probably the most theoretically correct way of handling risk. It's also, you'll see, a very difficult way of doing it. The probability analysis, we'll talk a little bit about it, is very useful, and it can give you probability statements, but it doesn't give you a good decision criterion. And ultimately, we're going to settle in this class for using an adjustment to the discount rate to account for risk, and we'll talk more about that. We'll probably end today talking about certainty equivalence. And this is more of a fun exercise than it is where you're going to be tested over it. But yet, because it's theoretically correct way of doing it, I at least want to introduce this idea to you. And what we want to do with the certainty equivalence is adjust the cash flows to their certainty equivalent. And let's say that we have a game and we flip a coin. And basically, if it comes up heads, you get nothing. If it comes up tails, you receive $100,000. Let's assume that you've got $100,000 in your bank account. How much would you pay to play this game? What's your expected value if you play it once? $50,000? You have a 50-50 chance, so you got a 50% chance of 0 and a 50% chance of 100,000. So your expected value is $50,000. Now, if you were in Vegas, you'd probably all pay me $60,000 to play. Because in Vegas, you know that the odds are stacked in favor of the tables. Okay, but you being rational beings and not the type that go to Vegas, meaning you're risk averse, how much would you pay to play the game? Now, I've made it simple by saying that you've got $100,000 in the bank. If you're rational, it's going to be something less than $50,000. How high would you go before you wouldn't pay anymore? You wouldn't go over 50 because you're rational and you're risk averse. About 25,000, 30,000, somewhere right in that range. That's your certainty equivalent. You're willing to let that certain amount ride, and you're indifferent between this prospect of having a 50-50 chance of getting 100,000 and 0. That's your certainty equivalent. Does anybody want to play the game for a cookie? How much money do you want to put on your line for a couple cookies? And I've got a coin here. I brought a coin. You put your money on the line. If it comes up heads, you lose your money and you don't get a cookie. What you going to put on the line?
I'll throw a quarter out there.
For how many cookies?
Just one.
Just one? So, and let's say that the cookie's worth 50 cents. So you're more hungry than you're rational. Okay, so we get to flip the coin. Let's see if he gets his cookies.
That's.
So you lose everything. Anybody else want to play? How much?
I'll pay 20 cents.
20 cents, okay. So assuming the cookies are worth 50 cents, then your certainty equivalent would be around 20 cents. See if I've got a loaded quarter here. That's tails. You could play enough of these games so you could figure out what your certainty amount is and how much the expected value is depending on the risk. That's what you would have to do for all of your cash flows in your investment to change all of those to a certain amount. So the certainty equivalent is the amount that makes you indifferent between playing and not playing the game. And then you discount those converted cash flows to their equivalent amounts that's based on the risk, their certainty, and what you're willing to take for certain. And then we could figure that out. Another way we can use is to look at the probabilities. And we can look at the variables that are contained in the net present value that we've talked about. And we can put a probability distribution around those, such as price. You have some expectations of what the price of corn or the price of wheat will be. You have some expectations of the price of fertilizer, the price of fuel, labor cost. You can then simulate the net present value based on those probabilities of the variables, and you can come up with the probability of the net present value. And you can then make some statements as to its expected value or its expected profit and the risk associated with it. For example, if you were comparing two investments and the one that's noted in yellow is investment A, and you looked at another investment that had a probability distribution that looked like this, you could see it. You expected a greater profit and there's less risk. So there's some statements that you can make about the investments when you simulate the net present value. The third way, and the way that we're going to use in this class, is what we refer to as adjusting the discount rate. We're going to adjust the discount rate for risk. That is, the required rate that you use as the discount rate is equal to the yield on other investments with comparable risk. In other words, the amount of money or the rate of return that you require on any project depends on the risk. And the riskier the project, the greater return that you are going to require to be compensated for the risk that you take. What we're doing then is we're going to add a risk premium to the risk-free discount rate. An example of a risk-free rate is the U.S. Treasury bill rate. It's risk-free, one, because it's short. It's a short term. It's not going to fluctuate or not likely to fluctuate much in that short period of time. And it also has the backing of the U.S. government. And probably in the near term, we don't expect the U.S. government to fold or to default on their debt, so it's relatively risk-free. However, the risk premium depends on the individual's risk-return preference and an individual's perception of risk. Each individual looking at the same project or the same investment may in their mind associate greater risk to that project than maybe another individual. Not only that, individuals that are more risk averse require greater compensation for taking risk. So those individuals more risk averse are going to assign a higher risk premium than another individual. That's why you see in the business world some businesses or some individual will take on certain risky projects where others won't. That's because they're not as risk averse. They don't assign as big a risk premium to the project. Okay, going back to the problems for classroom discussion now on the center pivot irrigation system that you can read in your handout. If we're looking at the after-tax risk-adjusted rate, and that's what we're going to be using now, in terms of the notation, the R is the after-tax risk-adjusted discount rate. This R with the superscript BT is the before-tax risk-free discount rate. And then this PREM, the prem, is the risk premium. And that's what we use to adjust for the risk. The M, as before, is the marginal tax rate. What was given in the problem, if you read it, is that this farmer requires 12.5% return, risk-free return. And for this particular center pivot irrigation system, this farmer is requiring a 2.5% risk premium. And then we multiply that by 1 minus the tax rate. So in this particular case, the pre-tax risk-adjusted rate is 15%. We multiply that by 80%, which is 1 minus the tax rate, to get 12%. So in this particular case, the farmer is requiring after tax a 12% rate of return to compensate not only for the time value of money, but also to accommodate for the risk associated in buying that irrigation system. Now, one of the things in this equation that I want you to understand, in some cases it's easier to come up with the 15% than it is to divide this into the 12.5 and then come up with a risk premium. Sometimes it's easier to say, well, for those type of investments, I expect to get 15%. Then if you know the risk-free rate, then you can calculate the risk premium. If you know the pre-tax risk-adjusted rate and you know the tax-free rate, then you can calculate what the risk premium is. So I'm just anticipating that when you get into this and you're going to say, well, what is the risk premium? How do I come up with that? If you start from the premises, you know how much you require on investments in that type of project, then you can back in to the risk premium. Okay, so now the analysis on this particular project. If you look back, we derived this formula a few periods back. It's in your notes, where we incorporated the inflation and we generated the cash flows. Now we're in the analysis part, where we have determined what the appropriate discount rate is to be, and now we're going to find the present value of each of the components. If we look at the present value of the cost, of course that's already in present terms, so it's $80,000. If we look at the present value of the after-tax net returns, you'll notice that they are not uniform, so we have to take each of these and discount them back at the appropriate discount rate for the appropriate period. So it's 1 period, 2 periods, and then 3 periods. We bring them back as single sum factors, add them up, and it comes out to $29,024. For the present value of the tax savings from the depreciation, notice that the depreciation is uniform. So we can use the uniform series present value factor at the 12% for 3 periods, and it comes out to $2,562. To find the present value of the after-tax terminal value, that's a single sum amount at the 3rd years. We discount it back using the single sum factor discounting for 3 periods. We add them up, and net present value then is $2,331. So even after incorporating inflation and risk, we've still determined that the center pivot irrigation system is a good investment, holding everything constant.